Welcome everybody. So now we're entering the last stretch of the course. In the next 4 weeks, we're going to be seeing now syntactical implication. Syntactical implication refers to formal proofs. So these implications that are not like this, like the ones we saw before, which were called semantical implication or the logical implication, which was like for every model, there's a model of this, a model of that. That kind of has semantic, that has a meaning to it. This one is kind of formal implications without meaning. So it's kind of purely syntactical, the manipulations of symbols, and that's how you kind of prove theorems formally. And we're gonna start first explaining how you do it. We're not gonna do it much because it's tedious. And then the important theorem that we're going to prove is the connection between syntactical side and the semantical side. Okay, so let's get into it. So this is an informal definition. This is not the formal definition yet, because I need to fill in a lot of gaps in this definition. But this is going to be the idea. So given a set of well-formed formulas, gamma, so here's a set of well-formed formulas, and a single well-formed formula phi, we say that gamma syntactically implies phi, and we write this symbol up here, if there is a formal proof of phi from gamma. Okay? So I'm just defining the word syntactically implies, and this symbol up here. We need to define what the formal proof is. So about this symbol is similar to that symbol that we have for logical implication, except that it has only one little bar instead of two. Okay, so one line is syntactical, 2 lines semantical. Hopefully that won't be too confusing. Cool, so let's try to figure out what all this means. Formal proofs. Our proofs are going to have only one inference rule. So that means that we're going to have some assumptions, and then we're going to work with them to get a conclusion. And what I mean work with, I mean apply this rule. So this is the only rule we're going to apply. And the rule just says this. If from a well-formed formula alpha, so alpha here denotes a well-formed formula, and another well-formed formula alpha implies beta, we may infer beta. That's it. That's called modus ponens. Okay, so that's everything else is going to go into the logical axioms, everything else that we might need. Okay, so that's modus ponens, which is going to be very important. It's the only rule that we have. And we are going to select, in the next video, not yet, because it's a bit messy, it's a whole set of well-formed formulas, lambda, of what we call the logical axioms. Okay, so gamma is going to be a set of well-formed sentences, actually. Or formulas, and that we call the logical axioms. We'll see it later. It's a lot of very basic assumptions, and once we have that, so now we're going to define what a formal proof is, which instead of proof, so not to get confused with when we do a proof or when we do a proof like in math, in the meta language, we're going to call these deductions instead of formal proofs. So a deduction of phi from gamma is the following. It's a finite sequence, alpha 0, alpha 1, alpha 2, alpha 3, up to alpha k, of well-formed formulas, where the last one is the one you want to derive, right? So essentially you're proving something and you're kind of making claims. This, and you make the next claim, and then the next claim, you make the next claim, and then you want to end up with the formula you want to prove. And it has to satisfy the following. So each alpha k either is one of your assumptions in gamma, or it's a logical axiom. So it belongs to the union of gamma and the logical axiom. So along your proof, you can say, oh, and now here I write something that I know from the assumptions and from the logical axiom. Or alpha k can be obtained from the previous lines using modus ponens. Okay, so what that means over there is that there exists and j less than k, such that alpha I is of the form alpha j implies alpha k. Okay, because in that case you can use modus ponens with alpha I and alpha j and you get alpha k. Okay, so that means previous lines, two lines that you wrote before, you can apply modus ponens to that and get the next line. Okay, so that means that's a deduction. So it's a sequence of well-formed formulas. Each one is either an assumption or an axiom, or it can be derived from previous lines using our inference rule modus ponens. That's it. Those are the formal deductions. So they're very simple, and there is no, it's super syntactical. I mean, all you have to check is that this has this form. Remember, this is just a set of characters, right? There is no meaning associated to this before you talk about models. If you're not talking about models, this is just well-formed formula. It's a set of characters. It's another set of characters, and if they have the right form, then you can write this thing, which is another set of characters. So essentially, you're just writing characters on a piece of paper and following very concrete rules, and there is nothing semantic about this. Or you're checking if one rule belongs to the set of axioms or the set of assumptions. Just check that they are the same. You have to just copy exactly the same without having to understand what your assumptions are about. Okay, so that's the formal deduction. And when such a deduction exists, we say that phi is deducible from gamma. Okay, so deducible means there exists a deduction of phi from gamma. Or sometimes you say phi is a theorem of gamma. Okay, so a theorem of gamma means exactly that there is a deduction of phi from gamma. And we write this symbol, the same one I mentioned before. In LaTeX it's called V dash, which implies that. Okay, so one definition and observation. So we say that a set S is closed under modus ponens. It's a set of well-formed formulas. So here S is a set of well-formed formulas. If whenever you have a formula alpha in S and you have another formula alpha that also belongs to S, then beta belongs to S. Okay? So that means being closed under modus ponens. If you have those two, then you have beta. And the induction principle is something you can actually prove that if S satisfies these two things, that is, contains the assumptions and the axioms, and S is closed under modus ponens, then S contains every theorem of gamma. Okay? So that's essentially kind of obvious, because the theorems from gamma are the ones you can get from doing these deductions. And essentially what's going on is that when you have a deduction, every step along the way is a theorem, right? Because if you cut a deduction in half, you still have a deduction, you still satisfy these rules. So essentially everything you're claiming along your deductions they're all theorems from phi, right? And essentially what you're doing is closing under modus ponens, right? Either you use something that you have already that belongs to S, or you use modus ponens. So if you want to prove this very, very formally, essentially what you have to say is, well, suppose that phi is a theorem of gamma. That means it has a deduction of some length, let's say length k plus 1, like this one. And then you have to do induction on k plus 1 to show that every phi that can be deduced with a deduction of length k plus 1 is a theorem. And then you say, well, if we know that this is true for all the previous ones, for the numbers below k plus 1, so that means that all alpha 0 up to alpha k, those all must belong to S. And then either if alpha k was obtained from the previous ones using modus ponens from the previous ones, they belong to S, so you have to belong to S. Or you just belong to S directly, right? So that's how you get that. If you didn't see that, try to write it down. Cool. So next we need to figure out what these logical axioms are. See you in the next video.